Namaskar. Today I will discuss the properties of orthogonal transformation matrix. Prove that product of two orthogonal transformation matrix is again orthogonal transformation. Solution: consider two successive orthogonal linear transformations of a rigid body with one point fixed, corresponding to cyclic two successive displacement of the rigid body, and are described by the matrices B and A respectively. We know that the two successive orthogonal transformation is equivalent to a third linear transformations described by the matrix C, where C is equal to AB and its elements are defined by Cij is equal to summation of Aij, Bkj, Aik, Bkj, where A is equal to Aik, B is equal to Bkj are matrices of the orthogonal transformations. This implies that summation of Aik, Akj is equal to delta Jk. Summation of Bij, Bij is equal to delta Ik, delta Jk. Consider now summation of Cij, Cjk is equal to summation of Aim, Bmj is equal to Aik, Bjk is equal to Aim, Bmj, Aik, Bik is equal to summation Aim, Ai1, Bmj, Bik is equal to summation of delta ML, Bmj, Bik is equal to Bij, Bik and summation of Cij, Cik is equal to delta Ik. This proves that the product of two orthogonal transformations is again an orthogonal transformations. Through the matrix multiplication is not commutative in general, but it is associative when the product is defined A B multiply C is equal to A multiply BC. Next example, show that in the case of an orthogonal matrix transformation, the inverse matrix is identified by the transpose of the matrix. Solution: consider an orthogonal transformation from xi to xi dash described by the matrix A and is given by xi dash is equal to summation of Aij xj, j is equal to 1 to 3, I is equal to 1 to 3, where A is equal to summation of Aij is the matrix of the transformation satisfying the conditions summation of Aij, Aik is equal to delta Jk. Let the matrix of the inverse matrix transformation from xi dash to xi be described by the inverse matrix A inverse is equal to Aij dash, where Aij dash are the element of the inverse matrix of the transformations satisfying summation of Aij dash Aik dash is equal to delta Jk. Also we have A into A inverse is equal to I, summation of Ai Aki aij dash is equal to delta kj. Now consider the double sum summation of aki, akj, aij dash, which can be evaluated either by summing over k first or over I first. Therefore, we evaluate the double sum as summation of aki, aij dash is equal to summation of summation aki, akj, aij dash is equal to summation of delta ij, aij dash. Summation of akj, aki, aij dash is equal to summation of aij dash, aij dash. Now evaluating the double sum over I first and then over k, we obtain summation of aki, akj, aij dash is equal to summation of summation aki, aij dash, akj is equal to delta kj, aki. Therefore, summation of aki, aij dash is equal to aij. From equation 5 and 6, we have aij dash is equal to aij. Therefore, aij dash is equal to aij. A inverse is equal to A transpose. This proves that inverse of inverse matrix of an orthogonal transformations identifies the transpose matrix. Example. Next example. Show that determinant of an orthogonal matrix is plus or minus 1. Let A be the matrix of the orthogonal matrix orthogonal transformations and A inverse be its inverse matrix. Then we have A into A inverse is equal to I. However, we know that in the case of an orthogonal transformation, its inverse is identified by its transpose. A inverse is equal to A transpose. Hence, equation 1 becomes A multiply A inverse is equal to I. Taking the determinant A multiply A transpose, determinant is equal to determinant of A into determinant of A transpose is equal to 1. Determinant of A square is equal to 1 as determinant of A is equal to plus minus 1, and this is so much.